Hello everyone. Today we are going to derive the Bose Einstein distribution. As we have already seen in the Maxwell-Boltzmann distribution and Fermi-Dirac distribution, we are going to consider an ideal system. So here we are considering an isolated system of n identical particles which are indistinguishable. That is, you cannot distinguish between particle A and particle B. Okay, and these particles, they are weakly interacting particles. Now we say that particles are weakly interacting because without any kind of interaction we cannot say our system is at equilibrium, right? In this particular case, our system is contained in a volume V at an equilibrium temperature T, and its total energy is U. Since we are talking about Bose Einstein distribution, the particles which will follow this distribution are bosons. Bosons have spin quantum number as an integer. The example of bosons are photon, pi meson, and also we know that alpha particle, deuteron, etc. are the example of bosons, right? Now these particles, they are weakly interacting, and the potential energy of the system we will consider as zero. That means only the kinetic energy contributes towards the total energy. Okay, as we said, these particles are identical and indistinguishable. That is, the mean separation between the particle is less than their thermal wavelength or the Broglie wavelength. Okay, so now let's go ahead and try to understand how we can distribute such particles. Now, the particles are having the spin as an integer, so they don't have to follow the Pauli's exclusion principle. So what we can do is that we can consider that there could be more than one particle in one common level. Now let's suppose that we have 1, 2, 3 and so on up to L states available for our systems. These L states have corresponding energy E1, E2, E3 and EL, such that with this energy is associated degeneracy G1, G2, G3 and GL. And the number of particles in these states are N1, N2, N3 and NL. Now the total number of particles for all the L state will be summation I is equal to 1 to L, NL is equal to N, capital N. And the total internal energy will be summation of Ni Ei for all the ith state. In our case, we have total L states. Since the system is isolated, the total number of particles and the internal energy of the system remain unchanged. Now we want possible permutation of all the Ni particles which are indistinguishable to be placed in Gi levels. Okay, such that they have freedom that any number of particles can be placed in any levels. Okay, so see, in this case we can expect that the system is like this. So if this is an isolated system within this box, okay, and let's say we have 1, 2, 3, 4 partitions. So see, this is partition number 1, this is partition number 2, this is partition number 3 and this is partition number 4. So we have 4 partitions and 5 levels: 1, 2, 3, 4 and 5. In these 5 levels, let's say we have particle 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 5 levels, energy levels, with 4 partitions between the levels, including 9 particles. Okay, so let's understand in this context. So we have Ni particles which are indistinguishable. We have placed them in Gi levels, in our case 5 levels, right? Okay, and there is a freedom that any number of particles could be placed in any level. So we have 4 particles in level 1, single particle in level 2, no particle in level 3, 3 particles in level 4, 2 particles in level 5. Okay, so we can say that the number of permutation of Ni particles among Gi levels is equal to the number of permutation of Ni particles and Gi minus 1 partition. This is one and the same. Again, let's take very simple example. So here we will consider two partitions. So we have two partitions, 1 and 2 and 3 energy levels. And we could distribute all these particles and we can calculate them by a permutation of Ni particles among Gi levels. So the permutation of Ni particles among Gi levels is the same as like arranging Ni particles in Gi minus 1 partitions. It is one and the same. Okay, so we can say that all the possible permutation of the particles plus partition is nothing but Ni plus Gi minus 1 objects that we want to deal with. Right. So let us understand what we have, what parameter we have to take care of. First, the number of ways of arranging Ni plus Gi minus 1 object is Ni plus Gi minus 1 factorial. Now let's focus on partition and particle independently. So the number of permutation for Ni particles among themselves will be Ni factorial, and the number of permutation of Gi minus 1 partition among themselves is Gi minus 1 factorial. Okay, that means if we want to find the number of independent permutation of Ni particles in Gi levels, it will be n factorial by r factorial into n minus r factorial. So we get Wi is equal to Ni plus Gi minus 1 factorial upon Ni factorial into Gi minus 1 factorial. Moving ahead, this is for one state with Gi degeneracy. Now we have to deal with L states. So the total number of distinct way of obtaining the distribution of particles among all the L states is nothing but the product of independent ways of arranging particles in each and every level. So it's a product. So we substitute the W's in this equation and we get the product I is equal to 1 to L Ni plus Gi minus 1 factorial upon Ni factorial upon Gi minus 1 factorial. Now we know that Ni and Gi are very large in this case because we are working with bosons. We can rewrite above equation as product I is equal to 1 to L Ni plus Gi factorial upon Ni factorial Gi factorial. You can neglect 1. Now we need to consider the most probable distribution. Now this kind of distribution among n particle and L energy state is possible when the distribution is maximum, that is W is maximum. So for large value of particles, we choose to maximize the logarithmic value of W rather than W itself. It has its own benefit. So let's do that. That means dl and W has to be equal to 0. Now going ahead with all the L state, we can rewrite this equation as del by del n1 for the state 1, that is the which has n1 particles. It is del by del n1 ln W del n1. Then for the state 2, it can be written as del by del n2 ln w del dn2. Using the summation, we get this equation. Okay. Now remember, since there is no change in the number of particles and the total energy, we know that from equation 3, that is summation I is equal to 1 to L dni is equal to dn is equal to 0, and summation I is equal to 1 to L ei dni is equal to du is equal to 0. That is, the energies of level EIs remain unchanged. Using that in this equation, we get this form. So here alpha and beta are Lagrange's coefficients which are associated with particle and the internal energy respectively. You can learn more about this separately. So we will go ahead with equation number 5. Now this equation must be true for individual increments of dni. For each level, terms in bracket 5 must be equal to 0. That is for level 1, 2, 3 and so on. So we'll consider the ith level for simplification. So the simplification for ith level can be written like this. Okay. Now going ahead, we are going to take logarithm of both the sides in equation number 4, which is the equation of W. And so ln W is equal to ln product I is equal to 1 to L ni plus gi factorial upon ni factorial into gi factorial. Going ahead, we can simplify further in this particular form. Okay, now using the Stirling formula, which is ln n factorial is equal to ln n minus n is equal to ln n by e to the power n. Ln w is equal to summation I is equal to 1 to L ni plus gi ln ni plus gi from Stirling's formula, and substituting such all other values using Stirling's formula, we can simplify further in this equation form. Now this is ln w on the left hand side. Okay, so if we differentiate ln w with respect to n, what do we get? We get this particular form where we have the general case for ith level. Okay, so let's do that. So when we differentiate it with respect to ni, what will happen is that all the terms except for the ith term would become 0. Okay, so you get a simplified form further in this form, that is ln gi plus ni minus ln ni, which becomes your denominator over here, and we give it equation number 8. So from equation number 6 and 8, let's go back to the equation number 6 for ith level. When we do the substitution and compare both the equation, we can write that ln ni plus gi upon ni minus alpha minus beta into ei is equal to 0. Further simplifying it, we can make subject of ni plus gi upon ni, that is number of particle and degeneracies, and we get the exponential term on the right hand side. Simplifying it further, we get this particular equation that is of our interest, which is ni is equal to gi upon e to the power alpha plus beta ei minus 1, which is known as Bose Einstein distribution of the particles among various states. So this is the derivation of Bose Einstein distribution. I hope you like this video. If you have any questions or query regarding this video, you can write it in the comment section. Like, share and subscribe. You can share with your classmates and friends. Vande Mataram.